In this video, I would like to talk about detectors in RayJack ONE. Detectors are used for radiometric or photometric analysis and many other tasks. Let me simply run this script here, which is about volumetric scattering, and explain what you see here. So here we have a collimated light source entering a sample with which is volume scattering. I use the so-called Gegenbauer model for that, and the scattered rays finally hit the screen which we would like to analyze. I think there is not too much to talk about the script itself, but here we have the phase function of the scattering material, which is essentially the angular distribution of the scattered light in a log scale. When we click here and go to linear scale, you see that really the dominant part of the light will be scattered into very small angles. Now, this is the main script. I load the system that I've shown just a minute ago. I initiate a ray tracer and trace. When you look here, you see that upon ray tracing, RayJack ONE gives you a summary table in which all objects are listed that were the last object in a ray path. So here you see it's the screen, but also the other surfaces. Here you have the number of rays, a very small number currently, and the flux. So when is an object the last object in a ray path? Either because it is absorbing or because the rays do not find further objects in their path, or for if some other stop criterion is met. So essentially, RayJack ONE already uses detectors for each object, but only for the flux. If you don't want to know more, you have to introduce detectors yourself. In order to do that, let me introduce a detector for irradiance. And this is done through the category detector. And here you see that there are various options: conformal irradiance, flux, intensity, irradiance. And let me talk later also about the ray collector, because it plays a key role for many analysis types. Yeah, detector irradiance. Then I have to enter a name. Let's call it irradiance again. And physical object, for which I use the screen you have seen and the pixel resolution in one direction. Now, if I do not specify an object here, the detector will act on all rays in the system. Alternatively, I could also assign here a list of objects. So you really have the choice. Now, let me run this script again with a, say, somewhat larger number of rays, and I do not want to see all of them, but maybe only one every 101st. What happens during ray tracing is the following. Whenever the ray tracer has a ray that hits the object to which we have assigned a detector, it will register it there, evaluate the irradiance in this case, and then the ray dies. That means the RAM consumption in the simulation is fairly low, and we call such detectors on-the-fly detectors. You can use almost as many rays as you want to make an analysis. Now, after the ray tracing, you can now look for the object named screen, go to detectors and click on the detector irradiance. Then you see the irradiance distribution on the screen. Alternatively, you can go here to analysis, select the irradiance detector, and here you have more options. For instance, you can smoothen, you can even do Fourier transforms, take out slices. Let me smoothen here twice and show you the result, which now looks nicer. And instead of doing that through the graphical user interface, you can as well use here a script, which is advantageous for making things automatic. Now, assume that we want to know not all rays on the detector, but only the rays that have been scattered only once. Then you can assign a so-called ray filter, and we set the number of scattering events to 1. So here you can use any Boolean combination of filters. Let me run the simulation again, and after a short while, we'll see the result, which is now noisier because we only see the single scattered light. You see sort of problem with that approach. Since the rays die after the ray tracing, you must ask the questions before the trace. Here, the question is how many rays, which irradiance is produced by single scattered rays. In many applications, it's better to ask the question only afterwards. And in my previous video, Introduction to Radiometry and Path Analysis, I've shown how to do that using post-processing and based on an object called detector plane. One word about post-processing. Here, post-processing is done if I use a detector with a name ray collector. A ray collector essentially just saves the rays that hit it, and so that after the ray trace, they still can be used for further analysis. I will get back to that in one of the upcoming YouTube videos. Now, let me go to another detector. Assume that we want to determine the optical path length distribution of the rays. In order to show them graphically, I create a histogram, which is a predefined data type in RayJack ONE, and let me start with 10 to 40 millimeters in 30, an interval of 30. Now I have to tell you what a ray actually is in RayJack ONE, and let me create a ray. Optical ray, there are different types of rays, and when I now press the dot, you see essentially what's contained in a ray, and it's quite a lot. So it contains the current medium, the current object of the ray, its direction, its initial direction before ray tracing, its flux, its initial flux, position, and many other bookkeeping parameters that you may use. And one interesting quantity is the optical path length of a ray. Now let me define a function in Python named OPD, which takes a ray as an argument, and add this ray to the histogram. On the x-axis, I add the ray optical path length, and on the y-axis, I add the ray flux. so that we really get a ray lux distribution. Now, in order to make use of that function, I create a detector, which I call OBD. It's a detector and it's a user-defined one. As always, we have to give it a name. I call it OBD. And then we assign it to the screen. And I now have to specify the evaluation function for which I use OBD. Okay. Now, after the ray tracing, I would like to show the histogram. And this is done with histogram plot. Let's run the simulation. And it should not take too long in this simple model. And we should now exactly get the histogram. You see that actually most of the rays have a rather short path length. This is due to the fact that the phase function actually is directed mainly in forward direction. So whenever the angle of the rays gets larger, there is more multiple scattering, and we get a more and more prolonged optical path length. So this way you can, with user-defined detectors, you can compute almost any quantity you want to extract from rays, but you should know at least a minimum about Python. Thank you.